Good afternoon. So I want to discuss with you this cassette plate design in Ideastica connection and answer you all of your questions that are focusing mostly on the model types. What are the discrepancies once you use one model type and second model type, and when to use basically the pro and what is the essential like behavior behind of the model types, but mostly some recommendation that you need to do in your Ideastica connection model to design your connection according to the expectation of the structural behavior of the cassette plates and the bracings. So this is the content actually where I want to discuss with you some symmetric gusset plates, analytical model, CBFEM, and summary, and mostly the eccentric gusset plate connection. What is the tailored and your case actually that you have a pain? Again, analytical model CBFEM. This article is coming from the verification that's been conducted actually on the real experiment. So we have like a data that we can compare. You will see the discrepancies in between the results. What is the error in between the numerical solution and the verification? And based on that are coming the recommendation to Idea Statica that that we will discuss. So, as is mentioned in the introduction, so basically the gusset plate connection is very often to join vertical and diagonal members in the truss or the braces. I do believe that you are doing, for example, both, so it will be valuable to elaborate it more. So. Actually, the eccentric gusset plate connection should be designed only if completely necessary due to the erection. Yeah, so this is just the I would say note from the author of the article. So we'll be also investigating the buckling phenomena that can happen on the structures and in the connections. So let me start at first with the symmetrical gusset plates and the analytical model. So once we are coming to, I would say, fixing the gusset plate to the member, you can see the gusset can have some like a two type of the I would say buckling shapes. So at first it's welded in the bottom, and the deflect shape and the critical length is equal to the length of the current gusset. But actually for the connection where are basically the bolts are penetrating the three plates, and the member SHS or RHS is connected or welded to the two pairs of the gusset plates, so the critical length will be increased and it behaves as a cantilever. So actually, based on these assumptions, you are basically able to calculate the critical length. You are able to calculate the buckling, but this is not the goal of this presentation actually. But ouch. But actually the goal is to explain you how to use it inside the IDEA Statica. So this is the model that is coming from our solution that is called idea statica connection. So the assumption is geometric linear stress strain analysis is not enough to design gusset plate connection of the compressed members. It must be complemented by the linear buckling analysis, and the results must be correctly evaluated. So you can see those are basically the shapes that are coming from the this is coming from the buckling analysis. Okay, so you are able to see the same trend that is basically in the analytical model explained. So actually, uh, the member type of the truss member should be set as a n with the n vy vz constraint. So it means that the bending moments are restrained. As I mentioned before, or I'm not sure if I mentioned, but those constraints, if you wanted to know what is happening once you turn it on, so all the rotations I mean the Rx, Ry, and Rz are prescribed as a 0. So it means there is no allowed rotation at the end of the condensed element. So yeah. So as we can see basically, so if you have like a just a single bolt, those constraints are necessary. Otherwise, the calculation will diverge. So this is just the phenomenon of the one bolt, but actually here at this example or verification, there is like a more bolts counted together. So and also the constraints NVY that has to be applied for correct buckling for correct buckling shape. So as you can see, here is some numerical analysis or numerical sim output from the those are the post-processing actually coming from the linear buckling analysis that are coming from the two tools. At first, it's ideastica connection. This is the part of the application or the particle from the portfolio of the idea statica that you are using for connection design. Idea statica member is basically the solution that you can observe here, where you are able to model as part of the connection with all the components as a bolt, welds, and yeah, contacts, for example, and actually also the member length. So once you have basically the full submodel, you are able to investigate what is happening either on the side of the connection, but also on the global part of the member from the point of view of the stability perspective, internal forces, stresses, and the strains. So once the thickness of the plate basically here is like a 6, 8, 10, and the 12 millimeters, what are standardly used thicknesses, I would say, you can see the critical factors and the compliance in between the solutions that is only on the in the part of the connection and in the part of the idea statica member, and which modes you had to like investigate to have a match. So at first, for thickness of the 6 millimeters, there is almost 100% identical critical modes and alpha critical. For thickness 6, 8 millimeters, as you can see, the same mode shapes has been found for second mode shapes in idea statica member and for the first mode shape in the idea statica connection. Actually, once we are coming to the thicker plate, so the discrepancies in between the critical factors coming to be higher according to the strength. So once I'm just coming scrolling down, um, we will receiving the summary, and actually I'm just talking right now about the symmetrical connections. Okay, the symmetrical gusset plate. So this is the summary that you should take it into account always in your model to um, have like a reasonable output and recommended output that is basically aligned with the verification based on the subsystem in the submodel coming from the ideastica member that is basically more precise because he is considering also the other part or the other end of the member and the stiffness of the connection on the other side of the column bracing uh, or the truss. So keep the free length of the gusset plate and the connecting plate as short as possible. So I will just approach to this point later on. Use the model type NVY for pinned members. So those are mostly when I'm treating. So here is mostly happening that it's behaves like a pin. And to calculate the connection using stress and strain analysis, this is the first step. There are some more steps that you need to consider. At first, run the linear buckling analysis and always double check what is happening with your um, with your eigenmodes and eigenvectors, so how it's basically deformed. So the 5 point, consider if the member to switch gusset plate is welded, may rotate and increase the possibility of sway buckling mode of the gusset plate. So if yes, decrease the buckling factor. There is no general recommendation actually. And the function of the member, unsupported line of torsion stiffness, gusset plate of the bending. If no, the buckling factor of the first mode shape utilize. Calculate the critical buckling length and make sure that the buckling load of the connection is higher than the buckling load of the connection member. So this is always what is basically happening, because the mostly is happening that the first buckling shape is the global buckling shape of the member, not the buckling shape of the gusset plate. So that's been the symmetrically, I would say, connected gusset plate.